think the last time I spoke was in 2014, so you now have 4 years of mathematics that I'll tell you about that I've done. So first, I guess I should kind of go back to some of the original ideas in contact homology and kind of talk about what are some of the difficulties and what are some of the non-difficulties, and then discuss sort of an alternate approach, and then eventually we'll loop back and connect back to sort of the original formulation by Yashberg, Giventhal, and Hofer. So as far as my notation is concerned, I'm going to let M2n plus 1 be a contact manifold. It's going to be oriented so I can globally describe the contact structure in terms of a global 1 form. And typically I'm going to assume that my contact form is non-degenerate. And then we know that the contact form.
So it would be in a Morse box sense, or just isolated?
Oh, it means that the eigenvalues of the linearized return map are not 1 for all the Rabe orbits.
Okay, so they're isolated.
Yeah, so isolated. So all the Rabe orbits are isolated. And then the Rabe vector field. By lambda of r is 1, d lambda of r is 0. So this is your normalization condition, and then this condition tells you that the flow of the Rabe vector field is transverse to the contact hyperplanes. And this gives us a splitting of the tangent bundle of M into the Rabe component at any point and the contact distribution at any point. And then for, I guess, some more terminology, gamma is going to be a closed Rabe orbit. And we say gamma is embedded or simple whenever the map from R mod Tz, where T is the period of the orbit, into the manifold M is injective. So in contact homology, we're going to care about the iterate of like all the embedded orbits, and then all of their iterates as kind of separate elements of the chain group. So we will also need to make a distinction between when the Rabe orbit is multiply covered and when it's embedded. And then because we have this nice decomposition, and because C is a contact structure, that means that we have a symplectic vector bundle when we pair C with d lambda. So we can extend a d lambda compatible almost complex structure J on C to 1 on the symplectization by taking J restricted to the contact distribution to be some d lambda compatible almost complex structure, and then we want J of the R coordinate to intertwine with the Rabe vector field. And J is said to be lambda compatible if these conditions hold. And so basically what's going on is that this is an extension of a almost complex structure on the contact distribution to one which is R invariant. And so this is going to be important when we start looking at pseudo-holomorphic curves in the symplectization, which we're going to use to build a chain complex. So I've got my moduli space of pseudo-holomorphic curves that I'm going to be interested in. So I'll have asymptotics on 2 closed Rabe orbits, gamma plus and gamma minus. And this is going to be the set of curves that are pseudo-holomorphic from R cross S1J into the symplectization. And then the pseudo-holomorphic condition means that the differential intertwines the complex structures. And then I need the limit So S is going to be my R direction and T is my S1 direction. So limit as S goes to plus or minus infinity of the projection of my curve to the R component of my symplectization needs to go to plus or minus infinity respectively. And then if I look at the limit as S goes to plus or minus infinity of the projection to the contact manifold of U, this is a parametrization of gamma plus or gamma minus. And then we're going to mod out by the automorphisms of the domain, which is R cross S1. And then I also have this translation on the target, so I'm going to also mod out by the R on the target. So we have J, gamma plus, gamma minus, is just M tilde mod R. And then the virtual dimension of Mj, this is going to be Conley-Zander index of gamma plus minus Conley-Zander index of gamma minus plus 2 times the first Chern class relative to some trivialization of the pullback of the contact distribution. And then we have minus 1 because we've modded out by this R action. So the idea that Yasha and Helmut and Giventhal had in 2000, so Ashberg, Giventhal, Hofer, they conjectured, among many other things, that we could form a chain complex which is going to be generated by closed Rabe orbits, and then the differential will count elements of a zero-dimensional moduli space. And it was called cylindrical contact homology because our moduli space of pseudo-holomorphic curves consists of cylinders, whereas in full SFT, you usually look at genus 0 curves, but they have an arbitrary number of negative ends. Right, okay. So the chain complex is going to be generated as a vector space over Q by good Rabe orbits. So I'll say what good Rabe orbits are in just a second. And then the grading is given by the Conley-Zander index of gamma plus n minus 3. So in dimension 3, the grading is Conley-Zander index of gamma minus 1. And coming back to this notion of good, well, basically what we do is we look at the, an embedded Rabe orbit, and then we can look at its odd iterates and we can look at its even iterates, and either the Conley-Zander index's parity is going to stay the same as you go between even and odd iterates, or it's going to change parity. So if gamma is embedded, then either CZ of gamma to the 2k mod 2 is equal to CZ of gamma to the 2k plus 1 mod 2, or they're not equal. And then in the latter case, the even iterates of an embedded Rabe orbit, where the parity of the even iterates is different from the parity of the odd iterates, these are said to be bad Rabe orbits. And all other orbits / iterates are said to be good. So in dimension 3, the negative hyperbolic orbits are the ones that give rise to bad Rabe orbits. So the even covers of negative hyperbolic orbits are bad. And there's kind of not the, I don't know, so it's a little bit mysterious why we have to exclude bad Rabe orbits from the chain complex. Part of this has to do with the fact that cylindrical contact homology is kind of like a orbifold quotient homology of the loop space, and so weird things are happening when we mod out by this S1 action, and this shows up when you try to orient moduli spaces which have asymptotics on bad Rabe orbits. It turns out that there's not a coherent way to orient those moduli spaces, and that has to do with the fact that basically when you look at the linearized return map, you're getting negative eigenvalues, and so this is going to end up screwing up what's going on with your Conley danger index, and then what happens when you try to orient your moduli spaces. And then I guess a slightly more satisfactory way to kind of see that you have to exclude bad Rabe orbits is you can actually write down a period doubling bifurcation. You can look at the chain complex before and after. And so in a period doubling bifurcation, you have an elliptic Rabe orbit. After the period doubling bifurcation, the period of that elliptic orbit doubles, and you also introduce a negative hyperbolic orbit of the same action as the original guy. And then its double cover has twice the period, and if you want the chain complex to be invariant, you end up having to exclude the double covers of your negative hyperbolic guy. So there's kind of like a variety of reasons why you have to exclude bad Rabe orbits, but kind of secretly it is because cylindrical contact homology is like a quotient homology of the loop space. Anyways, okay. So then the way that we'll define the differential is there's actually two different ways to define the differential. And the reason why there's two different ways is because if we take a cylinder in this moduli space, we can either encode the multiplicity of the top of the cylinder, or we can encode the multiplicity of the bottom of the cylinder. So there's two ways to define the differential. So the first way is to write this as, well, I write it as delta kappa. And so kappa is going to encode the multiplicity of the Rabe orbit. Delta is going to divide by the multiplicity of the cylinder. So we have dxy would be equal to the multiplicity of the top divided by the multiplicity of the cylinder. And then you have some choice of coherent orientations. Or you can define the differential to be first you divide by the multiplicity of the cylinder, and then you multiply by the multiplicity of the bottom. So you have that dxy is equal to the sum of m of y over m of u epsilon u. And then you kind of see what's going on. If I have a multiply covered cylinder, then that means that for some embedded Rabe orbits gamma plus and gamma minus, if I have the GCD of P and Q is 1 and gamma plus minus are embedded, then a k-fold cover of this cylinder is going to limit on, let's say, y is gamma minus to the kq and x is gamma plus to the kp. And so when you want to work out a gluing theory, or even if you're just trying to count sort of the ends of your moduli of your one-dimensional moduli space, when you glue sort of multiply covered cylinders together, there's going to be a number of different sort of choices, and it's not going to be sort of you're not going to get the right counts unless you multiply and divide out by multiplicities of Rabe orbits and cylinders. And what's kind of weird also about this theory is that we are defining it as a vector space over Q, but if we look at these coefficients, they're actually integral, because the multiplicity of the top is Kp. If I divide by K, I get P. Multiplicity of the bottom is Kq. If I divide by K, I get Q. So I do have integral coefficients, but somehow it's expected that you have to use Q coefficients. This would show up if you end up doing some kind of abstract perturbation scheme, but also kind of more generally, if you go back to orbifold Morse homology, you end up needing to work with rational coefficients. So there's some kind of like mysterious things going on that we don't quite understand, but that's okay. we'll see how to kind of change things a little bit and include both the good and the bad orbits, but we're going to end up working with different moduli spaces of pseudo-holomorphic curves, and our differential will not be as straightforward as I've written down here. So the conjecture from 2000 or the propaganda, depending on which person you ask, well, really which person, student you ask, they have different thoughts on how you should attribute results from Eliashberg, Hofer. So your students say that, well, Helmut is brilliant. Helmut knew that this would never work, so it's not allowed to be a theorem or a conjecture. They can say it's a propaganda.
Well, I view it as a propaganda thing.
So the
But of course, with possibility of success.
So if I have Chris Wendell or Joel Fish in the audience, I have to call it propaganda. If I don't have Chris Wendell or Joel Fish in the audience, I can call it a conjerum. And I guess if Yash is in the audience, you're supposed to call it a theorem.
Okay, I will find out the appropriate parts on the video.
I'm sure there'll be all kinds of hate mail in the comments of the video. Okay, so the statement was, assume no contractible Rabe orbits. Of index -1, 0, or 1. And this is not the Conley-Zander. This is this shifted index. So in dimension 3, you do Conley-Zander -1. Otherwise, it's something like +n -3, where the n appears in the dimension of your contact manifold. Okay, so you want to assume there's no contractible Rabe orbits of index -1, 0, or 1 that are associated to lambda, a non-degenerate closed contact manifold. And then you want to take J to be a generic lambda compatible almost complex structure. So another way that people say this is to say that you want an R invariant almost complex structure on the symplectization. Then the differential is well defined. D squared is 0, and the homology, which I'll write as CH, EGH, is supposed to be an invariant of the kernel of the contact form, so it shouldn't depend on the choice of contact form or complex structure. Lambda or J. Okay. So sort of the difficulty is that these moduli spaces can consist of multiply covered pseudo-holomorphic curves, and so then it's hard to guarantee transversality, and so there are some partial results in the cylindrical world. So let's see, Bao and Honda in 2015 came up with an invariant, a cylindrical contact invariant for hypertight contact forms, meaning there's no contractible Rabe orbits. And then Hutchings and I have a theorem from 2014 which says that if you're working with a dynamically convex contact 3 manifold, this means that C1 of the contact distribution restricted to 2 pi 2 of m is 0, and the Conley-Zander index of any contractible orbit is at least 3, meaning that the grading of all the orbits is going to be strictly greater than 2. Then the differential is well defined, and d squared is 0. Okay, so the difficulty that we the difficulty that sort of shows up is partly when you have these contractible orbits, you end up with a sort of failure of compactness, but actually this failure of compactness is a really good thing because Helmut used it to prove the Weinstein conjecture. But then, well, it's sometimes good. Sometimes it's bad, sometimes it's good. Kind of depends on your, your emotional mathematical state at the time. So the theorem that Michael and I have, it basically, we sit down, we grind through all these index calculations to show that some, bad compactness phenomenon can't happen in a symplectization. We show that you have index positivity in a symplectization because there's very nice iteration formulas for the Conley-Zander index in dimension 3, but it's not as well behaved in higher dimensions. And then also there's very nice automatic transversality results. So you can combine all of this, and we also use intersection theory in proving that d squared is equal to 0. But those arguments break down as soon as we go to a cobordism. So in a cobordism, things become difficult. So even when Bao and Honda sort of said, let's exclude all the contractible orbits, they still had to kind of do something where they made a perturbation in the neighborhood of any elliptic orbit to turn it into a hyperbolic orbit because they wanted sort of this uniform growth in the Conley-Zander indices. So in a cobordism, sort of life becomes very difficult, and it's clear that we need polyfolds to take us the rest of the way. So what Michael and I kind of thought about for the last 5 years is how can we come up with a contact invariant and make it well-defined without having to appeal to sort of virtual methods, and then how can we relate it back to sort of the original definition of Eliashberg, Giventhal, and Hofer. So that will be kind of the next idea. And so the, common theme in contact, or not in contact topology, but I guess a common theme in symplectic topology is always when you encounter pseudo-holomorphic curves and you have some regularity issues, you want to use like a domain-dependent or a time-dependent Hamiltonian. So what Michael and I did is we said, okay, let's try to use a domain-dependent almost complex structure. So it's going to depend on the S1 parameter of our cylinder. But when we do that, that breaks a lot of the symmetry, and so the obvious sort of differential that you write down will no longer square to 0. So we kind of have to go back to sort of ideas from classical Morse bot theory and think about what exactly is going on. So the idea is going to be use a domain S1 dependent almost complex structure so we'll let J, boldface J, be some family of lambda compatible J's that's indexed by the S1 parameter. And then what we'll do is we'll go back to this moduli space, and instead of using the time-independent J's, we'll use a time-dependent J. Okay, so make this a boldface J. Then this is a little jt for all t in S1. And I'm not allowed to mod up by this S1 action of the domain because I've use this domain-dependent almost complex structure. So this is just the R action on the domain. And then I need to mod out by the R action on the target, which is fine. But because I didn't mod out by the R action of the domain, the dimension of this moduli space is 1 greater than the time-independent guy, as is this. And so this -1 no longer appears. And so the first thing, so normally you can kind of make some assumptions so that we can ignore this. So when you're trying to count cylinders, you typically want to look at index difference 1 cylinders, because when we were working with the time-independent J's, the index difference would be 1, and then when you mod it out by R, you got to subtract 1, so you're looking at a 0-dimensional moduli space. But now I can't do that same sort of game, because if I look at index different 1 cylinders, I'm looking at a 1-dimensional moduli space. So that doesn't make sense if I want some differential to count things, because the differential needs to count elements of a 0-dimensional moduli space. So that's part of the reason why you can't just carry over this same definition. And then the other reason is going to be sort of a failure of compactness, because the next let me leave this here. Because sort of the next idea you can say is, well, how about I use evaluation maps to cut down sort of the dimension of this moduli space, meaning I'm going to look at curves that live in this moduli space, and then I'm going to impose a base point constraint. So the good news is that my moduli spaces are cut out transversely. The bad news is that the dimension is 1 greater. So the idea is to use evaluation maps to cut down the dimension. So I have my pseudo-holomorphic cylinder in a symplectization or a cobordism, and then I can look at the image of R cross 0. So here's my symplectization, R cross M, here's gamma plus, here's gamma minus, and then I'm looking at U of R cross 0, so that's going to be some line, and then I can look at sort of this top piece when I look at S going to plus infinity, and then I can look at this bottom point, and that's going to be where S goes to negative infinity. So I have EV plus minus are going to be maps before I mod out by the R action on the target, so it's going to be on M tilde rather than on M. And that's going to be to the image of gamma plus minus. So if gamma plus minus is multiply covered, I want to look at sort of like the underlying curve and just pick one point on that underlying embedded orbit. And EV plus minus of U is just going to be the limit as S goes to plus or minus infinity of pi M of U of S0. So at plus infinity, I'll get this point. So that's usually going to be P of gamma plus bar. And then this bottom guy is going to be P of gamma minus bar. So now I have point constraints, which I can use to kind of cut down on the dimension of my moduli space. And you can also think of using these point constraints to kind of force an S1 dependence on your Rabe orbits, because that's what you're basically doing in order to get that these moduli spaces are cut out transversely, because now they're all going to be somewhere injective. But there's sort of 4 different ways that you can impose constraints on a cylinder. You can either impose a point constraint at the top, a point constraint at the bottom, a point constraint at the top and bottom, or no point constraints. And so our differential is going to have to account for these 4 different possibilities of arrangements of point constraints. And Michael and I wrote out many, many pages of math to show that if you just took kind of this differential and naively reinterpreted it so that you put a point constraint on the top, and then you could encode the multiplicity of the top, that actually this would not square to 0, because when you compactify the index difference 1 moduli spaces, you have to account for sort of Morse bot buildings where you have a cyclic ordering condition that's not going to be present, and so you can't get that this will square to 0 if you just naively put in a point constraint at the top. Similarly, you can't get that this squares to 0 if you just put a point constraint at the bottom of your cylinder. So you really do have to sort of enlarge your chain complex and think about sort of a non-equivariant version of contact homology, but that kind of hopefully makes sense because we've broken the S1 dependence by using this family of S1 dependent almost complex structures. And so that really sort of should suggest that we're doing something non-equivariant, and so we need to, at least make sure that it looks a little bit more similar to symplectic homology or something. And
So those things that you just mentioned that you could try to do, but then the differential would square to 0. If you did that, does the square of the differential have a straightforward algebraic interpretation?
So if you have sufficient regularity in dimension 3, we can show that certain components of the non-equivariant differential will reduce to sort of this expression and this expression when you're looking at going between 2 good Rabe orbits. But because there's also going to be bad Rabe orbits floating around, you won't be able to sort of always write down exactly what the right answer is. But I'll also talk about that in a little bit. Okay, so classical, I guess, Morse bot theory. Guides us, and so our non-equivariant chain complex is going to be generated by 2 copies of every Rabe orbit, and we're going to use sort of formal symbols, gamma check and gamma hat. And here, what do I want to say? So the chain complex is generated by 2 formal symbols associated to each Rabe orbit. So you can think that sort of the original theory proposed by Heliashberg, Giventhal, and Hofer is kind of degenerate in a certain sense because you have this S1 symmetry. And so what we're doing is breaking this S1 symmetry by using domain-dependent almost complex structures, by using point constraints. And so if you think about what that says in sort of just Morse bot world, if your bot manifolds are all circles and you put a height function on them, then to each of those degenerate circles, you'll get a minimum and a maximum, and those will be the generators for your theory. And so formally, you can think of sort of the minimum and the maximum becoming arbitrarily close together, and then that will give rise from your sort of degenerate circle to 2 formal symbols. The hat is going to have its index shifted up artificially by 1, and then the minimum is going to be the check, which has the same grading as the original Rabe orbit. So we have that gamma check has the same grading as gamma. Gamma hat is the grading of gamma check plus 1. You can think of gamma check as being an element of the 0th homology group of the image of gamma, and you can think of gamma hat as being an element of the 1st homology group of the image of gamma. And then you're including both the good and the bad Rabe orbits, which is nice because that will allow us to kind of capture torsion coming from bad Rabe orbits. And it's also maybe a little bit more holistic seeming because we've now sort of incorporated both the good and the bad Rabe orbits. The reason why sort of this wasn't like the natural choice for Yasha and Helmut was because Helmut had previously studied time-independent moduli spaces of pseudo-holomorphic curves because he was interested in dynamical questions and looking at sort of compactness issues forcing the existence of closed periodic orbits. And so when Helmut developed his, Fredholm theory for pseudo-holomorphic curves and symplectizations, he wasn't thinking, oh, I'm going to build a homology theory out of it. He was trying to answer nice dynamical questions. But of course, as Helmut says, once you start throwing moduli spaces of pseudo-holomorphic curves around, everyone starts salivating like Pavlov's dogs and trying to create a Floer theory. So this is maybe like...
There's also, what is interesting, in the symplectic homology case was actually quite opposite. So we started actually taking time-dependent perturbations, and then later one put, not doing this, you get an equivariant theory.
Yeah.
So here was sort of the other. I mean, of course, in some sense, which was never published actually before the non-equivariant theory. There was actually an equivariant theory in order to explain Eckland-Hofer capacities, but that was never written down. So, I mean, also never worked out.
Sometimes you can be a man ahead of your time or your theorems. Okay, great. And then, let's see. Okay, so then the other thing I'm going to have to do is for each embedded Rabe orbit, we will make a generic choice of base point P gamma, and we'll put an overline bar to sort of indicate that we're looking at the image of gamma inside of the manifold M. Okay. And then, what do I want to do? Okay. So then what I can do is I can write down a differential, and it's going to have 4 terms in it. And you can sort of reinterpret it formally in terms of this gamma check and gamma plus, which you can also then reinterpret in terms of using the evaluation maps to put base point constraints on your cylinders. So it gets a little bit gross looking, but we'll call this DNCH. This will be a map from NCC star to NCC star minus 1. It's going to have 4 components. So we'll have check, hat, plus, and minus. So if we think of how matrix multiplication works, you would think of this eating a check and a hat and then spitting out check or hat accordingly. So I'll write sort of down what each of these guys counts in terms of moduli spaces, point constraints, and then also like a picture. So I don't know, like guideline is that a hat has a constraint at the bottom if on the minus infinity end a check has a constraint at the top if on plus infinity end. So when you write a paper, you can't just like sort of draw pictures. So we look at 4 sort of different moduli spaces. So you have an alpha and a beta, and then you have like check, check, hat, hat, and then you've got check, hat, and hat, check. All right. So basically, what these moduli spaces are going to consist of is elements of these domain-dependent moduli spaces that then have point constraints imposed. So if I see a hat, on the negative infinite end, like so this guy and this guy will have point constraints at the bottom. This guy and this guy have point constraints at the top. Let's see, this guy has no point constraints. This guy has 2 point constraints, and this has a point constraint at the top. This has a point constraint at the bottom. And then that kind of corresponds to D check is going to count elements of this guy. D hat is going to count sort of elements of this guy. D plus should count elements of this guy, and D minus should count elements of this. And what will also be interesting is that we'll need an obstruction bundle gluing term for D minus when we're working with contractible Rabe orbits. So let me try to write out a little bit more about what's going on with each of these terms. And also I can relate some of them if you can pick your family of almost complex structures to be equal to the same J for all time, if there's enough transversality to do that. Okay, so the first guy, D check, this is going to count, we'll want the index difference between the Rabe orbits alpha and beta to be equal to 1. And this differential will be equal to the delta kappa alpha beta if alpha and beta are good. And you could pick J to be equal to the same J for all T in S1. But if that's not the case, then you're going to be counting cylinders with a point constraint and then more spot buildings in general. So you're going to count cylinders. You have your point constraint at the bottom, and then you don't impose a point constraint. Or sorry, you have a point constraint at the top, but you don't impose a point constraint at the bottom. So this is going to count curves in MJ alpha beta such that ev plus of u is equal to this generic choice of point constraint that I pick ahead of time in terms of a base point on all of my Rabe orbits. And I'll also have more spot buildings with a cyclic ordering condition. So I can have things like this, or I can have sort of, I'll, for action reasons, end up needing to have a finite number of levels. But basically, you have your point constraint at the top, then you've got another, like wherever ev minus goes, then you've got ev plus of your curve, and then you've got p of some intermediate orbit. So you want sort of a cyclic ordering to, with respect to your Rabe flow on that orbit of ev minus of the preceding level, ev plus of the next level, and then the generic base point on the intermediate level. So you have a cyclic ordering condition with ev minus of ui, ev plus of ui plus 1, and the base point of the intermediate the base point of the intermediate Rabe orbit. And so you can keep kind of doing things like this. Okay, so you're going to have to count like these kinds of buildings. The nice thing is that you can actually compute this in dimension 3, because the work that Michael and I did to show that the Eliashberg-Giventhal-Hofer differential makes sense. We said that you could do that with a time-independent J, and so what that will do is it will make it so that you can't have any of these buildings for sort of index reasons. And then because you've got this base point here at the top, that's basically encoding sort of the multiplicity of that Rabe orbit, and then you still have to account for the multiplicity of the cylinder. Well, that's kind of why you end up getting this expression. Whereas when we look at D check, we're going to be looking at these moduli spaces, and so there's going to be a base point constraint at the bottom, and so we're going to be picking up the sort of multiplicity of the Rabe orbit at the bottom. So I guess it's kind of nice that you can actually see what's going on with the various terms of the differential. So d hat, alpha hat, beta hat. This again has index difference 1. This is equal to negative kappa delta alpha beta if you can use a time independent j. And this counts guys with a base point constraint at the bottom, plus the Morse bot buildings, where the very last level needs to have a base point constraint at the bottom. And then, let's see. And then, all right, let's see. D plus, what do we want D plus to have? Okay, so D plus has a check and or a hat and a check, and the index difference is going to be equal to 0 because there's going to be no base point constraints. So you'll get these kinds of curves. There's no base point constraint, plus Morse bot buildings with no base point constraint. They just have to have the cyclic ordering condition. And we have that d plus of alpha check, the coefficient of the differential from alpha hat to alpha check. This is going to look like the map that you see in symplectic homology, where you'll get 0 if alpha is good, and negative 2 if alpha is bad. So it kind of looks, it sees basically the 2 torsion from bad ray orbits. And then the last term is this d minus plus an obstruction bundle gluing term. And the reason why the obstruction bundle gluing term appears is because when you look at d squared, because of the sort of increase in the dimension of the moduli space, when you multiply the differential matrices together, the entry in the bottom, like right-hand corner, ends up counting index difference 3 cylinders. And so you can show that actually there's going to be some interesting sort of compactness phenomenon arising. And then Michael's obstruction bundle gluing from his work with embedded contact homology tells us sort of that we need to have some sort of a correction term so that the obstruction bundle gluing that shows up actually gives us the right count in terms of our differential. So let me try to say a few words about that. So d minus alpha check beta hat, so that's going to be index difference 2, because we're going to have 2 point constraints. And these are going to have a point constraint at the top level and a point constraint at the bottom level. And then we need an obstruction bundle gluing correction term. And what's happening is when we look at d minus d check plus d hat d minus, this is going to count index difference 3 cylinders. And so what can happen is if you have an elliptic contractible orbit, then you can't exclude its branched cover. And so this is going to be like a gamma to the d plus 1. This is going to be a gamma. This is going to be a gamma to the d. This is going to be a branched cover of a trivial cylinder over gamma. This will have index 0 before you mod out by the R action. This will be a trivial cylinder. This is a cylinder of index difference 1, and this is a holomorphic plane of index 2. And then we also have a point constraint. So we have a point constraint at the top, and then we have a point constraint at the bottom. Okay. And so this obstruction bundle gluing term is basically going to say that if we look at the checked gamma d plus 1 generator to gamma d, we're kind of thinking of this as our gamma d plus 1 with a check because there's a point constraint at the top, and then there's a hat gamma d at the bottom because there's a point constraint at the bottom. This is going to be equal to the number of index 2 planes asymptotic to gamma. Modulo r, and here you can actually use time-dependent j in this case to figure out what's going on, because you can have a time-independent sort of like holomorphic building bubble. And what's kind of remarkable is that you can actually compute the number of elements of this moduli space in terms of a winding number. And so this is going to be the degree from the map between the moduli space of index 2 planes modulo r to S1, which is C minus the origin, mod r being positive. Well, it turns out to be a circle. So it's kind of this really cute thing that pops out of all of the work that Michael did with Taubes to do obstruction bundle gluing for ECH, because basically we can show that there's just one kind of irritating building showing up when we restrict to the 3-dimensional case, and because there's just this one type of building, you don't have sort of all these like horrible combinatorial things to write down, and because it really just has to do with the holomorphic planes of index 2, you can really get a hold on what that sort of correction term has to be. So that was kind of fun. Okay, so then now I can state, I guess, the theorem that Michael and I will put up on the archive once we finish checking orientations. Okay, so you either assume that m to n plus 1 lambda admits no contractible Rabe orbits, or the dimension of m is equal to 3 and lambda is dynamically convex. Then if J is a generic S1 family of lambda compatible almost complex structures, then the non-equivariant differential is well defined. It squares to 0, and the resulting homology is actually only dependent on the kernel of the contact form, so it does not depend on the choice of J or lambda. Okay. So then the question is, how do we relate this back to the Eliashberg-Giventhal-Hofer definition? And sort of the good news is that we've introduced time-dependent almost complex structures. We've sorted out all this kind of gross business with point constraints. We have some obstruction bundle gluing term up here. And so what we do is we say, okay, there are these really nice family Fleur ideas which date back to Helmut and Fleur when they were thinking about symplectic homology. And we can kind of mimic these same ideas here. And then, as I was trying to kind of allude to, if we have sufficient regularity in dimension 3, it can be possible to pick our family of almost complex structures to actually just be time independent, and then that allows us to kind of simplify the differentials, and that's going to allow us to show that sort of all but 2 of the differentials in this formal Borel construction will vanish and allow us to relate it back to the Elie-Ashburg-Immental-Hofer theory. So try to quickly say a few words about the Borel construction. And family Fleur methods. Okay, so now we need to use a bigger family of J. So let script J be something that depends on both S1 and ES1, because we're going to do some sort of Borel construction. And this is going to be a S1 equivariant S1 cross ES1 dependent family of lambda compatible almost complex structures. So that seems like a terrible mouthful. It kind of is, but it's not too bad because other people have thought about this, and then it's kind of a matter of adapting these ideas. So now we put a script J here, and then because we're working with S infinity and CP infinity, what we can do is we're going to have sort of hybrid pseudo-holomorphic curves that depend on sort of the Morse flow line parameter between critical points on CP infinity. So now my moduli space is going to have gamma plus a Rabe orbit, and it's also going to have a critical point on CP infinity. So I'm going to have x plus minus are critical points of a Morse function on CP infinity, and you can just take the perfect Morse function on CP infinity. And then we have gamma minus, x minus, and then this is going to be pairs of curves. So we're going to have a curve and a flow line. So we're going to have an eta and a u, such that eta is a map from R to ES1. This is going to be a flow line. Then my J-holomorphic curve equation, I'm going to have to incorporate this flow line parameter. So I'm going to have dsu plus jt eta of s dtu equals 0. Then I need the limit of the projection to be plus or minus infinity as before. I need this guy to be a parameterization of gamma plus minus. I also need that the limit as s goes to plus or minus infinity of eta of t is equal to the inverse image of x plus minus. So these are going to be lifts of critical points on CP infinity to S infinity. And that should be enough. Then I'm going to be modding out by automorphisms of R and S1. So the R comes from, there's an R action because I have flow lines and I'm also in a symplectization still. And then there's an S1 action coming from the S1 equivariants of this family. And so the dimension of this moduli space is going to be Conley-Zander index of gamma plus minus Conley-Zander index of gamma minus. And then we're going to have the Morse index of x plus minus the Morse index of x minus. Okay. And then okay. So then the theorem is that we can use this to get an S1 equivariant moduli space. That we use this S1 equivariant moduli space to come up with an S1 equivariant version of non-equivariant cylindrical contact homology. So we'll assume the same as in this theorem. Okay. Star plus, we now want J to be this S1 equi ES1 cross S1 dependent family. Then I can form a chain complex by taking the non-equivariant chain group, tensoring it with the cohomology ring of CP infinity, which is just Z drawing U, where U is some formal variable of degree 2. And then my differential is going to be D0 tensor the identity plus D1 tensor U inverse plus an infinite number of terms, where the U term, so there's going to be sort of two terms in each of the differentials. One term is going to decrease the grading on the formal variable by an appropriate amount, and then the other term is counting elements of the K, this counts elements of the K-dimensional moduli space. So we're going to have that the index difference between these two critical points is going to be K. So this gives us a plus K, and then you would be basically looking at index difference 0 pseudo-holomorphic curves. And so this is going to give us a chain complex. Which does not depend on the choice of J or lambda. And then the other nice theorem that we can prove is that in dimension 3, in the dynamically convex case, we actually have enough regularity to define this chain complex. We can take J to be equal to some S1 independent object, and that will be exactly the same thing that we sort of need to define these moduli spaces, but everything sort of simplifies. Then we'll get that D0 looks like kappa delta negative delta kappa, and I have my D plus my D minus, and then I have that D1 of alpha check is going to be kappa of alpha check if alpha is good, and 0 otherwise. I'll have that D1 of alpha hat is equal to 0, and dk is equal to 0 for all k greater than or equal to 2. And as a result, there is a canonical isomorphism with the S1 equivariant contact homology with this time-independent J. So this depends on M, lambda, and J. We tensor it with Q, and we'll get the contact homology defined by Eliashberg, Giventhal, and Hofer, lambda J. And we'll also get invariance of this theory because we know that if we take a small ES1 cross S1 dependent family of almost complex structures that's sufficiently close to this time-independent guy, we can use this theorem to say that it's actually an invariant and it didn't depend on the context structure. So if you tensor it with Q, this is still technically an invariant, and so that gives us invariance of the Eliashberg, Giventhal, Hofer theory. So I'll end there.